Microservice architecture has transformed the development landscape for both web and mobile applications, offering a paradigm shift in its stateless nature and loose coupling. This innovative design allows for creation of native mobile applications that leverage the same backend services during web application frontends. The concept of building once and utilizing multiple use cases has become a prevailing norm in enterprise design patterns. To address the scalability demands of numerous calling clients, notable strides have been taken in containerization and orchestration strategies, particularly on public cloud platform. However, these scalable design techniques have inadvertently increased the exposure of backend services to potential security threats, expanding the attack surface and associated risks. On top of it, the mix of heterogeneous technologies in microservices architecture, their distinct logging strategies makes the central logging difficult, which in turns loosen the security. Additionally, the complexity around building the resilience for fault tolerance across the decentralized networks adds to the security loopholes. These simple security designs, which were once used with traditional web application, cannot be used for microservice based applications. Unlike traditional web applications, simple security designs are insufficient for microservice based applications. This necessitates a re-evaluation of security strategies to address the unique intricacies and challenges introduced by the distributed nature of microservices. This video articulates the innovative approach to meet the security requirements inherent in safeguarding distributed services within the microservices architecture, offering insights into tailored solutions for the complex security landscapes of microservices based applications. Traditionally, all the web applications were designed as monolithic in nature. In that traditional setup, MVC, which is model, view, and controller, was the most popular paradigm. Applications would have a web server where all the static content like HTML, JavaScript, and images was hosted. In an internet-based web application, these web servers are deployed in the DMZ network layer, and the web application code itself is compiled and packed as an enterprise archive file, ER file, or a web archive file, which we call WAR file, right? This archive file is deployed on the enterprise application servers like IBM WebSphere, BA WebLogic, JBoss EAP server, or Apache Tomcat server, widely used to name a few. These servers are deployed in the organization's internal network and shielded from being directly exposed to the internet. This archive file would communicate with the backend databases, other data stores, or would integrate with third-party services using web services or asynchronous integration mechanisms. As it can be understood from the diagram that the number of entry point to the backend layer are very limited in monolithic design structure. Not every layer or a component of the application is exposed to the outside world, and none of them would accept requests directly from outside. In a typical web application, all the input requests are scanned for security at the web server level, for example, using LDAP system for user authentication. Once the request is authenticated, it then passes down to the application level. At this level, the requests are further filtered by a servlet filter. This security check verifies whether the incoming request is associated with a valid session identifier or not. If not, it challenges the incoming request session to authenticate first. Further, the authorization checks may be in place to validate that the requesting user has the necessary roles and permissions to access the intended resources. The intercepting servlet filter carries out such tasks centrally to make sure that only authenticated and authorized requests are dispatched to the corresponding resources. Internal layers and code blocks may not be concerned about the legitimacy of the request. They can be confident that if a request ends up there, all the security checks would have already been taken care of. On top of it, since these are stateful applications, the internal components can acquire the user information at any point of time by querying the web session in hand. It is the servlet filter which injects the incoming user information into the session variables during the initial filter process. However, the security design cannot be so simple in case of distributed microservice based architecture. With the advent of cloud platform and discovery of containerization techniques using Docker and orchestrating software like Kubernetes or Docker Swarm have complicated the problem even further. Let's understand the design complexity in securing microservice architecture. Microservices architecture deals with breaking down the application to smaller and independent deployable units for getting a number of benefits as mentioned on the screen. To start with is a service isolation, separation of concerns, horizontal scalability and containerization, quick build cycles, easier maintenance, isolation of failures, and cloud portability, etc. This design has helped to solve many issues with the traditional monolithic applications, but at the same time, it introduced the following security challenges. Since the logic layer and middle tier of the application is splitted into so many smaller and independent pieces, the attack surface has significantly increased. Also, due to the loose coupling of the front-end and back-end layers, it permitted multiple front-end systems to talk to back-end services, and this has also broadened the attack surface. With the rise of Internet of Things, many automated devices started interacting with the microservices layers since there is no human interactions involved in this data transfer. Authentication and authorization are not straightforward. Due to these reasons, legacy techniques which were once used for protecting the monolithic web applications can no longer be used in case of microservice architecture. Since the backend microservice can be widely distributed, they can be present in a single data center or a cloud environment or a combination of data centers and public clouds. On top of it, unlike monolithic, the front end and back end are totally detached, and the backend service can now be written in heterogeneous technologies. For example, few services might be running on Java language and other might be on Node.js or Python. The microservice architecture at a high level can be visualized from this diagram. Now let's understand how to secure the microservices. Traditionally, security teams have always focused on protecting the databases, network, and infrastructure layers. But with the introduction of distributed microservice architecture, the attack vector has shifted to the server side of applications. This is evident from some of the major cyber attacks which occurred in recent times. A robust security design for microservice architecture needs to focus on these five main areas. First, securing the attack surface. As explained in the earlier section, the attack surface has snowballed in recent times due to the proliferation of the services using their containerization designs and auto-scaling features on public clouds. Front-end systems are isolated and can most likely to more than one. unlike the traditional design where backend and frontend are packed as one unit. For securing the distributed microservices, which are segregated from the front-end systems, there needs to be an authentication and authorization mechanism which can generate the tokens which are short-lived. The movement towards this approach caused software teams to look for security tokens that worked with RESTful and JSON format. Some of the token technology that involved from their requirement includes, JSON Web Token and OAuth 2.0. Also, to reduce the exposure of services to the caller, there needs to be a single point of contact which can route the calls to the appropriate backend service. This gave a way to API gateways. This diagram describes the high-level design for using the token-based mechanism using API gateways. And here is a high-level flow which explains how the token mechanisms can protect the backend services. User requests the protected resource which is hosted on a microservice. Frontend checks if the valid token is present. If not, it sends the user to login page which has multiple authentication challenges depending on the organizational need. Once a user enters the authentication credentials, a call is made to the authorization server via the API gateway. Authorization server authenticates the user credentials by validating it with the identity provider. This can be any LDAP system present in the organization. If the credentials are valid, the authorization server returns a short-lived access token along with a refresh token to the front-end system. Front-end stores the refresh token. It calls the resource server again by passing the access token in the request header. API gateway has a filter mechanism which first validates the access token by firing an authorization check with the authorization server. If the check passes, the request is sent to the microservice for delivering the request needed by the user. If in case the access token is invalid, the authorization server denies access, which is handled by the front-end system as a message on the login screen. In case the access token is expired, the front-end system can request a new access token from the authorization server by passing the refresh token. If the refresh token is invalid too, then the front end can request the user to re-log into the application. This entire cycle gets repeated with every request by the users. Second is defense in-depth implementation. As we know the problem statement, backend services are of various sensitivities and priorities. It cannot be one size fit all strategy for all the services. Depending on the microservice, the level of security should be changed. For example, there may be public read APIs which can be exposed to all callers. There can be other services which can be exposed once the caller is authenticated, and there can be some other premium services or admin services which not only need to be authorized based on the user profile but also be protected carefully. Simple security token service with API gateway cannot be a solution for this need. For handling this kind of services, a strategy like defense in depth needs to be employed. Defense in depth is a concept in which multiple layers of security controls are placed throughout the system rather than a single defense system across all layers. For the use cases where an extra level of security needed to be needs to be implemented for premium or admin services, there can be an additional layer of security in the form of private API gateway, which is not exposed to callers directly. This needs an additional filter and authorization scheme. If a caller needs to reach this inner secure layer, they need to access via facade services and pass an extra level of authorization as shown here in this diagram. Third is principle of least privilege. Due to the database per service pattern, each service is independent of the other, including the databases. For a transaction which joins multiple domains, services need to talk to each other either directly or via orchestrating Sega patterns. Many times, inter-service communication is complex to implement. Such design would need to be intricately done. It is a challenge to narrow down the rules which govern the privileges and permissions for the APIs involved in the services. API needs to be designed based on the principle of least privilege. Access needs to be given only to those users who are not only authenticated but authorized to access the API. API access only needs to be granted based on the need. Start with the minimum access and only extend based on the need. Fourth is encryption everywhere. Services can be decomposed efficiently using various governing principles like common closure principles and single responsibility principle to achieve the maximum isolation, but the inter-service communication is unavoidable as the transaction span across multiple entities. Encrypting the data at rest using technologies like metric transparent encryption or by using the secure keys which are rotated once in every few days might solve this security needs to the for the data at rest. Also, the storage buckets for the files and caching mechanism should be encrypted using secure password. Not only the data at rest, but the data in transit should be encrypted using certificates and SSL layers. And the fifth area is continuous scanning, monitoring, logging, and implementing DevSecOps. There are various other problems deeply embedded in microservices architecture since all the services are stateless, independent, and heterogeneous. There cannot be a uniform logging pattern and framework. This makes threat identification difficult. The other challenge with most development teams is the early identification of the vulnerabilities before they creep to production. And also designing the security around the containers and various components is a complex challenge. So here's a solution. In case of microservices, it is imperative and essential to design a central log aggregation solution. This would also help narrow down the issue faster and avoid corruption to other layers and services. Along with these employs appropriate SAST, which stands for Static Application Security Testing, and DAST, which stands for Dynamic Application Security Testing scans, would mitigate the issues upfront. Also, the methodology of DevOps should shift to DevSecOps, where development, operation, and security team makes a combined call on microservices architecture rather than dealing with the siloed approach. Constant monitoring and feedback mechanism may be employed for better result. So we have seen some of the important concepts which are needed for securing the distributed service architecture. However, securing these services in a microservices architecture is a relatively continual process. A lot of research is also being done in the field of AI where the threat can be forecasted based on the ODTs in the service requests, responses, or interaction pattern. These forecasts can be validated using the machine learning techniques to come up with mechanisms to avoid the infiltration. At the minimum, the service can be shut down by invoking the circuit breaker and alerting the responsible parties. Future scope of work including devising the innovative techniques to implement the multi-factor authentication based security which don't have any human interaction. That's all for this session. I will come up with more informative and interesting topics. If you have found this content informative and enjoyed this session, please like and share this video. And if you have not subscribed to the channel yet, please subscribe and enable the bell notification to stay updated on the latest content. Your support is highly appreciated. Thanks for watching.